Okay, thank you. My name is Nadav, and this is Arnold, and we're here to talk to you about vectorization in LLVM. So, to the left, you see a list of projects that vectorize LLVM, LLVM-IR. These are out-of-tree projects. So let's start with the first one. NESL, it's an academic project. They vectorize OpenCL style code. It's by Sebastian Hack and Ralph Karnberg. Intel OpenCL, another project very similar to the NESL project with outer loop vectorization. They also work on LLVM-IR. Poly, a lot of you know Poly. It's an LLVM-based project. If you go to poly.llvm.com, you can learn more about the Poly project. Unfortunately, the Poly buff is right now in a different room, but it's a great project. And ISPC. I ran into Matt Farr, the creator of ISPC, earlier today. And so ISPC is a great programming language. It's a domain-specific language, and they vectorize during IRGen. So they look at the AST and vectorize while they lower to LLVM-IR. So all of these projects are vectorizers that are outside of the LLVM repository. A lot of them are 5 or 6 years old. But to the right, you have the list of vectorizers that we have inside the LLVM tree today. So the first vectorizer is Hal's BB vectorizer. And Hal is awesome. He wanted LLVM to be a high-performance compiler, so he wrote the first LLVM-based vectorizer, the basic block vectorizer. And he talked about it, I think a year and a half ago in the European LLVM developers meeting. And I encourage you to go and look at his slides and the videos. So this was the first LLVM-based vectorizer. And in the last year, we developed 2 new vectorizers, the Loop-vectorizer and the SLP Vectorizer. So we couldn't have done it without the help of the community. We have an amazing community, and as soon as we started developing these vectorizers, a lot of people reached out to us and helped, and it was really great to have all of the support in the community, and we couldn't have done it without you. So thank you. Thanks, everybody. So now we have 2 new vectorizers. And let's see why it's important, why it's so good. Well, we have a list of workloads here that benefit from vectorization. We have anything from 1x to almost 3x boost in performance. These are real applications in the LLVM test suite that benefit from vectorization. So when you enable these 2 new vectorizers, the Loop-vectorizer and the SLP Vectorizer, then you boost these programs. Now, we vectorize programs from a lot of different domains. A lot of the programs here are from the domain of linear algebra, and it makes a lot of sense. You just go over arrays, and it's really easy to vectorize. But there are some other interesting programs, such as media encoding and compression and just general code, and it's really great. But you're probably asking yourself, all right, so on a few benchmarks, you're showing us great performance, but are there any regressions? Well, let's take a look at this slide. In this slide, we have all of the programs in the LLVM test suite that are affected by vectorization. If we vectorize, the performance moves up or down. And this is the S-curve. The red line indicates no change, 1x. Anything below the red line is a regression. And if you look all the way to the left, you'll see a few regressions. And if you look all the way to the right, you'll see huge performance swings. I imagine that LinPack is somewhere around here to the right, and around 2x boost in performance. But there are regressions. We have regressions. So later on today, we'll talk about the cost model. So we have a cost model for deciding, is it worth vectorizing? And we decided to be very conservative about our cost model and our decision. We could have vectorized a lot more workloads, but we'd also have a lot more regressions. And we decided to be conservative and vectorize only loops that we know are going to benefit from vectorization. Loops and SLP code that we're going to talk about later. So, now you're probably saying to yourself, this is great. I'm hooked. I want to use this vectorizer. Well, the two vectorizers are already enabled by default on OS, O2, and O3, with a slightly different set of features for each one of these levels. For example, on OS, we don't want to increase the code size too much. So we disable some of the features of the loop vectorizer. On O2 and O3, we try as hard as we can to vectorize. And if for some reason you want to disable vectorization, then you can use -F no vectorization, or -F no SLP vectorization, or -F vectorize to enable it back. Okay, so now Arnold's going to talk to you about the first vectorizer, the loop vectorizer.
Okay, so we've heard about that we support two vectorizers. Let's start talking about the loop vectorizer. The loop vectorizer vectorizes innermost loops. It takes scalar instructions, widens them to SIMD vector instructions, and it also unrolls them. It's kind of a similar concept. We take one scalar or vectorized instruction and widen it to 2 or more instructions. Next. All right, let's look at what kind of loops can we handle today. So we handle loops with unknown trip count. We handle loops that count backwards. You can imagine you have function calls, 2 parameters, 2 pointers. We don't know anything about those pointers. They could overlap, and sometimes that's unsafe. So we insert runtime checks to make sure it's actually safe. We can handle reductions, accumulate a value that we maybe read from an array. We can handle inductions, store the induction variable to an array, for example, or do some math on it. We can handle loops with control flow. Typically that's called if conversion. We can handle pointer and C++ iterators. We can vectorize those. In this example, we see the STL accumulate function. We handle partial vectorization. What we mean by that is, in this example, we have an access that might access a load that might access every kth element, and so you can't do this as a vector instruction, which means we have to scalarize this load. We handle vectorization of mixed types. In this example, we have an integer array and a character array, and we store it to the integer array. Next. We can vectorize some function calls today, and I'll talk a little bit about this later. And we also, as I mentioned before, unroll for ILP during vectorization. In this example, we have a reduction, and we vectorize that. Okay, so we've heard about some features that we support, some loops that we can handle. Let's look at how have we implemented that. So the loop vectorizer consists of 3 phases. First, we check for legality. We look at phi nodes, and we need to classify them as either inductions or reductions, or we have to give up. We look at memory accesses in the loop. Are the memory accesses in the loop safe to vectorize? We also look at function calls. And if we understand the semantics of the function, we might vectorize it. So once we decided it's legal to vectorize a loop, we go and look, is it profitable? We create a cost model, and if we decide it's profitable, well, finally, we will transform the loop, we will vectorize it, unroll it, or we will just unroll it. So the first phase, legality. As I said, we look at phi nodes. We classify them as either inductions, so that's the I in green here, or as reductions. We accumulate a value. We have to handle those differently. Next, we look at memory accesses. I have an example here where the scalar version copies the first element to the second element, and then copies the second element to the third element. So what happens here is that we set the memory in the array, the elements in the array, all to the first element. Now, what would happen if you would vectorize this as is? Well, you would take the first 4 elements, you would copy them, move them over by 1, and then walk 4 ahead and repeat that. And as you can see, the effects on memory is different. So you need to be careful when you do vectorization that you handle this right by not vectorizing it. As I mentioned before, sometimes we have a loop, and the pointers in the loop are parameters to a function. So we don't know anything about them. And in this case, we have to add memory checks. So we recognize during the legality phase, yes, you have to add memory checks. And later on, we will see, we will omit those. And finally, we look at function calls in the function. And if the function call is recognized as an LLVM IR intrinsic, we can vectorize it. Next. Profitability. We've decided it's legal to vectorize. Now the question is it profitable, right? So we go over the instructions in the block, ask what is the scalar cost of doing this. We have a cost model that can answer this question. We add all of those up. And then we try different SIMD vector widths. And again, we ask the same question. What is the cost of doing it vectorized? And based on comparing those numbers, we choose to vectorize, or we choose to keep the loop scalar. I have an example of an API call here from the cost model. We can ask, for example, what is the cost of this arithmetic instruction? We pass an opcode, for example, an add, and we pass a type, either a scalar I32, or let's say for a vector type of 4 I32s. Okay, I've mentioned the cost model. So what is that? How does it work? You can imagine that writing down the cost of every instruction for every target would be extremely tedious and a lot of work. But this information is already in the backend, and the backend provides an interface to query this information. So for example, we have API calls to ask, is this operation, is this add legal, or do we have, or will the backend promote it, implement it in terms of other instruction, or change the type? You can imagine we could also have vector widths that are wider than supported by the target. Let's say you had 16 I32s. Well, on your typical target, you will have to split that up. So again, there's an API call that will tell you, okay, we'll have to split that up into 4 of those 4 times I32 vectors. So we can use this as a multiplier. And we have generic rules in the cost model. They're not fully accurate, but they should give an idea. We start off with a cost of 1. If the target tells us, well, I have to expand that operation, we set the cost to 2. We query for the legalization cost. You have to split the vector into 2 vectors, so we multiply by that. Or maybe we have to scalarize the whole thing. Well, then we multiply the cost by the vector width. Sometimes that's not good enough. Sometimes you have to specify for your target that certain operations have a certain cost. And in this case, we fall back to tables. Okay. At this point, we've decided it's legal, it's profitable. Let's vectorize this loop. So we started off with a scalar loop. Now, when we vectorize a loop, as I said before, we have to make sure that in some situations that pointers don't overlap. So we create a skeleton that will check, do my pointers overlap? Can I even execute the vector loop once? Because you can imagine sometimes your iteration count is a parameter, so you don't know, is it going to execute 4 times, is it going to execute 256 times, is it just going to execute 3 times? So in this case, if it just executes 3 times and you decided on vectorizing it by 4, you jump around the vector loop and just execute the scalar loop. So in this example, we see at the top, we have this memory check. In the middle, we have the vectorized loop. It's an example where we see a reduction, and that reduction is unrolled, and we'll hear about that a little bit later. And finally, at the very bottom, we have the remainder scalar loop that will execute the remaining iterations that we couldn't do vectorized. Okay, so I've talked about unrolling. Nadav will tell us a little bit more about that.
Okay, so why do we unroll during vectorization? So modern processors support out-of-order execution, which means that at every given time, there are several instructions that are in flight that can potentially be executed together. Unfortunately, some types of code prevent out-of-order execution. Why? Because there are dependencies between the calculations. So if you look at the loop that we have right here, the sum calculation is the addition of the current sum with the sum of the with the value that we're adding. And this calculation depends on the addition from the previous iteration, and the iteration before, and the iteration before. So we can't execute these additions in parallel, only the loads. So out-of-order processors issue multiple iterations of the loop, and they create this structure of data dependency. And each addition depends on the addition from the previous iteration, and all of these instructions sit in reservation stations, and they're not being executed because there's some sort of dependency that prevents them from being executed. By unrolling the loop, we create two independent chains of calculations, and the add instructions can execute together in parallel, and this allows for more instruction level parallelism. As you can see in the example here, in the green you have one addition, in the blue you have another one, and they go and they're executed together. Now you're probably asking yourself, well, we have an unroller. Why are you unrolling inside the vectorizer? I mean, it doesn't make sense. Well, the analysis is pretty similar, and when you think about it, SIMD, single instruction multiple data, it's kind of ILP, kind of instruction level parallelism, because you're executing multiple scalars at once. And the analysis that is required for vectorization is the exact same analysis that you need to do in order to vectorize these kind of loops, reduction loops. You need to be able to know, can I execute multiple iterations of this loop at once? Will it be beneficial? How do I check for dependencies? How do I add the remainder loop? So all of these things are very similar to vectorization. And so our loop vectorizer is actually a loop optimizer. And for many loops, we decide to unroll only because the cost model says that it's not worth to generate SIMD instructions. For other loops, we only vectorize because we have register pressure, and you know, this is something that we estimate, and then we decide not to unroll. And for other loops, we both unroll and vectorize.
All right, we have heard about features that we support today. Let's talk about some features that we might want to add in the near future. So on the top of this list, we have support for vectorizer pragmas. I'll go into a little bit more detail in the following slides. I'm just going to list a few of them now. Vectorization with library functions, inlining and restrict, vectorization of interleaved data. We also want to be able to give feedback to the user when and why we didn't have vectorized the loop. And as we've heard in the poster session outside, we also want to support new processes like the AVX 512 that have features like predication of many instructions. Vectorizer pragmas. We want to give our users the ability to specify vectorization parameters like the vectorization width or like the unroll factor, because sometimes they simply know better. And today, they have to use Clang vector intrinsics, and if they want to change the unroll factor or the vectorization width, well, then they have to rewrite their whole loop, let's say. So by having a pragma, that becomes a lot easier for them. Also, in certain situations, we can't tell that the memory accesses in a loop are safe or that no runtime checks are needed. And again, a vectorizer pragma could help out here and could specify that it's actually legal to vectorize that. And then we can omit runtime checks, or we can even tell that it's legal to vectorize that loop. Vectorization with library functions. So today, we only vectorize if the functions are math intrinsics, and because of the cost model, also only if there is an efficient implementation of the target ISA. So let's say a POW function, which I think is not available on x86, well, we will not vectorize that today. But as you can imagine, on many platforms, there will be efficient implementation of vectorized versions of those functions available. So wouldn't it be great if we could use them? Inlining and restrict. So I talked about memory checks and overlapping pointers. Restrict is a way of specifying that accesses through two pointers cannot overlap. That's a little bit simplified, but at the high level, that's what it boils down to. And yes, we support that today. LLVM-IR has that as function parameter attributes. But once we inline, because this information is only available on function parameter attributes, this information gets lost. So we would like to add support for sub-function level attributes or some form of communicating this to the compiler. And there's been some discussions on the mailing list about that. Vectorization of interleaved data. The vectorizer works by looking at each instruction individually. So if you look at that loop, you'll see plenty of memory accesses. And if you look at just one of those memory accesses, let's say the B, you'll see that this access is not consecutive, right? We access every second element. So when we come to estimating the cost of doing this, and also the way we generate code for this is that we will gather that this data, essentially we will emit 4, so we're vectorizing by a vector factor of 4. We will emit 4 loads and 4 inserts into a vector per access that you see here. So that is inefficient, and the cost model will tell us so, and we will not vectorize this loop. But if you look at this loop, at the accesses in this loop a little bit in more detail, and if you look at all of them at the same time, you will see that there is actually a consecutive access going on, and that you can vectorize that a lot more efficiently. Namely, if you vectorize it by 4 vector loads, some interleaving operations that will store the data from those loads into vector registers like we need, and then some de-interleaving operations plus 2 vector stores. And again, there's been some discussion and some bugs on the mailing list, respectively in Bugzilla. Okay, so we've talked about loop vectorization. Nadav will tell us a little bit more about SLP vectorization.
Okay, so the SLP vectorizer is the second vectorizer that we implemented this year. And it's quite different than the loop vectorizer. And there's a picture of a tree, and I'll explain why in a little bit. So SLP stands for superword level parallelism. And the idea is pretty simple. So we have all these scalars in the code, right? Every time we do an arithmetic operation, we have scalar. Why don't we take all these scalars and put them into SIMD vectors? I mean, should be possible, right? Well, this is the idea of SLP vectorization. You take the scalars, you group them together into SIMD instructions, and you improve the performance. So if we look at the example that we have right here, we have 2 consecutive loads. We have 2 add instructions, 2 consecutive stores, and we also have some constants. Then this is the perfect example for SLP vectorization, what we can do is we can take these two constants, put them in a vector, load two doubles from memory in one 128-bit SIMD vector, add them to the constants, and then save them again in one SIMD instruction. That's great. And potentially, maybe not for x86 in this case, you can reduce code size and also register pressure. So this is a very beneficial optimization. And this optimization is very beneficial for games. Why? Because you have a lot of graphics. And in graphics, you're using RGBA. Great. RGBA. Each one of these components go to a SIMD element. Same with physics simulation, except that we only have 3 dimensions, but just details. Also, linear algebra. We have matrix multiplication here. So this is great. We get a 2x boost in performance on this code. Why? Because we have all these consecutive access to memory. We're storing consecutive elements, and we have all these scalars that we can add together into SIMD operations. And 2x on this workload, it's by the way, it's one of the workloads from the LLVM test suite. So how do we do it? How do we merge all these scalars together? Well, we create trees. We say that consecutive stores are the roots of the tree. It's easy to find consecutive stores, and we have other roots. And then we look at the operands of the stores. And then we say, oh, they're both add instructions. We can merge them. Let's look to the left branch. 2 consecutive loads, perfect. Let's look to the right. 2 constants, great. So this is a vectorizable tree, and we can vectorize it. That's pretty simple, and that's the idea of SLP vectorization. So let's look at the entire process. First, we build a vectorizable tree. Then we estimate the cost of the tree. It may not be beneficial to vectorize it. We may not have the right SIMD instruction. But once we figure out that vectorization of the tree is beneficial, then we just simply take the group of scalars and turn them into a single vector instructions. And that's SLP vectorization. So where do you start building these trees? Well, the easiest thing to do is to find consecutive stores. We scan the code and look for consecutive stores, and then we start looking up, build these trees. Arithmetic reductions. A lot of times we have loops that were unrolled, and then you have all these arithmetic operations, and we try to build trees from these chains of additions or multiplications. When we get desperate, we start looking at phi nodes and start swizzling them around and try to look for other phis. And there are also other very common patterns that we're using to find these trees. Okay, so let's talk about some of the features. So if you look at this tree right here, on the left side branch, you'll see that there's one scalar that is used by 2 other scalars. But we don't want this to prevent us from vectorizing the tree. So we broadcast the scalar into the entire vector. So this is one of the features that we have. To the right, you see that there's a multiplication and division operation, which we can't fit in the same SIMD operation because they're different. So what do? We gather these scalars into the same SIMD vector, and then we vectorize the rest of the tree. And of course, we have a cost model to estimate the cost of the gather and the broadcast. So we support these things. The next important feature is vectorization of multiple basic blocks. So the branches of the tree can be in multiple basic blocks, which is very interesting because we also vectorize phi nodes. And the one example that I can think of is code from the C++ standard library. So somewhere in the implementation of std-map, there's code that loads 2 pointers from memory on one basic block, load 2 pointers on another basic block, and then there's a phi node, or 2 phi nodes actually, and then 2 stores. Well, this is great because 2 pointers fit perfectly into an XMM register. So we can load this data, create a vector phi node, and then save it back to memory. So this is an example of how support for multiple basic block can accelerate general code that's not necessarily games or graphics or physics. Okay, another example is this. If you look at the add operation in the middle of the tree, on the right you have a plus. On the left, you have the multiplication. But if you look at the node right next to it, it's the other way around. Luckily, we can sweasel, we can commute the plus operation, and we can reorder the tree and to make sure that all of the pluses are on the right side, all of the multiplications are on the left side, and we can vectorize this whole tree. So this is one of the features that we have. And we support diamond-shaped, well, it's not trees, it's DAGs. Well, it's not really DAGs too, because we support multiple basic blocks, and the branch may come back from behind and connect to the middle of the tree, so it's a graph. Really, we vectorize graphs of nodes all over the function. So this is also an important feature that we have. Sometimes we have scalars that use values in the middle of the tree. And this is really, it's really easy to generate code for it. I mean, we have the CMD vector, we pull out the right element, and we generate code for it. But there's another problem. So the LLVM-IR, it's not a DAG, and unlike selection DAG. So when we vectorize, we have to move instructions around. And we may break the correctness of the program if we don't reschedule the entire function. I mean, not only one basic block, we have to basically reschedule all of the instructions and arrange the right order for everything because, well, we vectorize across multiple basic blocks. So it's really difficult to implement the general support for external users, external scalar users without having a DAG. So we have some restrictions on this feature. But if we know that it's safe, then we support and vectorize this code. But the work is not done. We can still improve the SLP vectorizer. First of all, we can support, we should add support for vectorization of function calls. Power, sine, cosine, we should be able to vectorize that. Cost model. So right now, the cost model for vectors that are not a power of 2 is not very accurate. And we have some regressions, and we decided to be conservative. So we disabled vectorization of not power of 2 vectors. Loop-aware multi-basic block vectorization. So we have this tree that spans multiple basic blocks, and maybe some of these basic blocks can be inside of a loop. So we may want to assign a different cost for the basic blocks that are inside loops. We don't have that right now. And we always need to find more roots or more patterns that expose vectorizable trees. So this was the SLP vectorizer. So today we talked about 2 vectorizers, the Loop-vectorizer and the SLP vectorizer, and you can help. So it's still a very young project. We started about a year ago. So the code base is fresh. It's a lot of fun, and it's a great opportunity for new people to come and contribute to LVM. So how can you help? You can analyze programs. If there's a program that you care deeply about, just try to vectorize it, see what happens. Compare it to other compilers, run benchmarks, try different configurations, SSE4, AVX, maybe different ARM processors, different vectorization widths. If you're a code-gen person, you can improve either the cost model or code generation for vectors. And if you find a missing feature, then write to the mailing list and we can work together on implementing this feature. And that's it. So, thanks. Any questions?
Questions?
Ivan?
While loops, can you vectorize stir copy?
I'm sorry?
While loops, can you vectorize stir copy?
Yes.
Okay.
We can vectorize, yes. While loops, yeah, and copy, yes.
Well, not copy, string copy.
String copy.
Copy until you hit a 0.
Yes, we have runtime checks for checking if the source and destinations don't overlap. Without this check, we wouldn't be able to vectorize, so.
When you were talking about the unrolling reducers, Is it an issue that the accumulators might be changing the associativity when the accumulators are floating point?
So there's no problem with integer.
Right, integer is fine, obviously.
Integer is fine. We don't do that for floating point for correctness.
Okay.
Unless we do support fast math mode, so we will.
Right. Sketchy math.
Yeah, we will unroll it if we're using fast math.
Second question, sorry, I'm trying to do it while I have the mic. If I was going to try to activate these and not, using Clang, in my own set of optimization passes, like what are the gotchas? What are the names of these passes, and are they just called vectorized pass, and then
just grep through the code for vectorize, and you'll find the real.
Are there any gotchas there? Do they have to be before or after? For example, the unrolling, right? You might already be unrolling and then re-unrolling. Does that have to come in a particular order, or should I just leave out unrolling loops altogether if I'm going to do your unrolling pass?
So the vectorizers happen pretty late in the optimization pipeline. The loop vectorizer is the last loop optimization, and the SLP vectorizer happens before. You may want to clean up the code before you run the vectorizers.
Okay.
We can talk offline.
Okay, thank you.
Sure. Do you want to answer some of them?
Hi. You said in one of the later slides that you had problems working at IR level. Sorry, you were working at IR level and things would be easier if you had a DAG. Why don't you just use the selection DAG?
The problem with selection DAG is that it works one basic block at a time. And we wanted to be able to vectorize across multiple basic blocks.
ICC has had vectorization for a very long time, as you know. How do you compare in terms of what you vectorize and the quality of code you generate, the speedups that you get?
Yes. ICC has a good vectorizer. I think that generally they vectorize more code. On some loops, we outperform ICC on x86.
ICC, I think, performs loop nest optimizations, which we don't. We just vectorize innermost loops. We don't do any loop restructuring at this time.
I can answer the question earlier. So if you want to know which passes you have to pass before the loop vectorizer, go on the tests, and then you see how we call opt, and then you pass like inst combine or other things. So if you want to know what things you need to pass before, if you don't want to pass the whole thing, just look at the tests and they will tell you.
Yeah.
A question about the pragma. When you add the pragma, will it mean that you will have to vectorize even though you think it's illegal? Or are we going to check for legality and cost?
So the exact syntax is not set in stone. You can imagine that you could have a pragma that says that it might be legal, please check for me, but you could also imagine a pragma that says it's legal, don't do any checks.
Right.
Yeah. I think that will be an interesting discussion with the community, how exactly that pragma might look like.
Okay, one last question.
Do you happen to know how the speedups from the two vectorizers split out? So you showed a slide showing the speedups. Is one of them more important, or is it kind of equal?
The loop vectorizer is a lot more important.
Thanks.